Hello, welcome to the first tutorial for ECE425/525 Digital Integrated Circuit Design. This first tutorial we will walk through the basic setup of the Cadence system, building a CMOS inverter, and doing some simulations. So first of all, you can see that I'm using a Windows platform. This is actually my personal laptop. So I will be logging in remotely to the PSU server system to access the Unix desktop. So in order to do that, you'll need a couple things. So you'll need to download PuTTY and VNC Viewer. They're both free. PuTTY is a terminal emulator, allows you to connect to the ECE server. VNC Viewer, VNC standing for Virtual Network Computing, allows you to control another computer's screen. Both of these are very useful, but they won't allow you to actually copy any files from the PSU server down there. So if you want to copy files to your desktop here for writing your report and whatnot, there's another free program called WinSCP, Windows Secure Copy. I like to use it. It gives you kind of a Windows GUI interface and allows you to kind of drag and drop files rather than working through a terminal, if you're more comfortable with that. Basically, you can get any information regarding how to connect remotely to the PSU server system by visiting the CAT website. So the CAT website, you just go to the platform you're using. So I'm using Windows, and those of you that have a Mac or whatnot, to go there and look down over here on the left. It'll actually tell you how to remotely access the server system. So you kind of see right here, it kind of gives you some of the information to get started. So very useful. You will see on this CAT website that it actually tells you can log in using the Win32 system. I've used it before. I don't recommend it. I prefer the VNC Viewer better. It's a little slow, so you do get some lag time on the Win32, and you don't get that on the VNC Viewer. So visit the CAT site if you have any more information on how to remotely log in. Okay, so I've remotely logged in using VNC Viewer, and as you can tell from being down in the lab, this is your basic screen you see when you log into the terminal down at PSU in the lab. So this is a Unix desktop. For those of you that aren't familiar with Unix, it's basically the Solaris operating system created by Sun Microsystems. It's a little different, and for those of you that use Windows a lot, not familiar with it, it takes a little bit getting used to, but you'll get the hang of it. So first thing you're going to need to do is you're going to need to go to the 425/525 website. You're going to need to download a couple things. The first thing being is this Cadence 610 folder. All right, that contains Cadence, what we're going to actually run our simulations and whatnot with. Next thing you will need to download is the 50 nanometer models file. Okay, basically it has all the information of the devices that we're going to simulate with. So once you download these to your desktop, what you're going to want to do is you're going to want to actually move these files over to, and once again for those of you that are not familiar with Unix, so this U or this /U/ your username, that's basically your home directory. Okay, that's where you're going to want to basically come in and stick the folder in the file. So what I did is I placed the Cadence 610 folder here, and then I placed the 50 nanometer file inside it. Once you've done that, everything should be good to go going forward. So let's go ahead and get started. So if you come over and you right click on your desktop, you will get an open terminal. Open terminal is used in the Unix system basically to put in commands that allows you to do things. So this is where you will be coming to open up Cadence and get started with your labs. So when you first come in here, you will need to type this in, but once you've been once you've done it a few times, very cool feature. It actually saves your previous input commands. So all you have to do is arrow up, and it will show you your what you've actually previously typed in. So the first one we're going to start with is this CD Cadence S610 /. So the CD being change directory. So you're going to change directory from your default home directory to the Cadence directory. Go ahead and hit enter. Next, what we're going to do is we're going to go ahead and want to put this command in, source setup all .bash. So source being run this file, the setup all .bash. So that's actually going to run the setup file. Okay, the next thing we want to do is type in ICFB followed by space and the and symbol. This starts Cadence up for us. Go ahead and hit enter. It'll take a little bit of time for everything to load up. Okay, so first thing you're going to want to do once you get to this screen here is you're going to want to go back and go ahead and hit yes to this box that always pops up with, you're not get a license. Just hit yes. You won't be able to do anything until you tell it yes. So another screen will pop up with what's new in Cadence Virtuoso 6.1. Don't really care. Okay, so first couple screens you're going to see here. All right. So the first one is the log screen. This gets actually useful once you're simulating and checking your schematic for problems. You built your schematic. You're going to save your schematic, and there's you run a check and a save, and there's something wrong with the schematic. You left a floating node. It's gonna tell you what you did wrong on the log screen here. So it's a pretty useful screen. The other one you'll see is your very basic starting off point, the library manager. Okay, this is where you're gonna basically create your library and your cell, and then inside your cell a view. Okay, so it kind of hierarchy goes from over here down to here. So for our library, since this is our first tutorial, we're going to create a basic CMOS inverter. So let's go ahead and get started there. We'll go to File, New, Library. So let's call this Inverter Test. Okay, for technology library, you're going to want to select attach existing library. Okay, so this is what we use here in 425, 525 simulations. It's a free PDK 45 nanometer. So basically it's our tech library. Okay, so this is the technology that we're using, is the 45 nanometer technology. So that will be your smallest width. It technically will be 50 nanometers, but it's the 45 nanometer technology. You'll see what I mean later. Okay. Leave everything else the same and hit OK. So now you can see that we've created a new library over here. Okay, so once we've selected that library, let's go back up here to File, New, now Cell View. Okay, so for our cell, we're first always going to start off with a schematic. Okay, so let's just call it inverter underscore test 1. Okay, and then leave everything else the same. Type is schematic. Hit OK. Okay, so now this window pops up. It's our Virtuoso schematic editor. So now we're going to go ahead and I'll walk you through some of the toolbar features, and then we'll start on our inverter. So The first one being over here is your check and save. So once you've built your schematic, you always select the check and save, because it first of all saves your schematic and also checks it for issues like floating nodes, stuff like that. Okay. You have a move, copy, a stretch, delete, edit properties, and these are all things you could select your instance on the schematic and then edit properties and change some of the parameters and whatnot. You have your undo and redos, your zoom in, zoom out, zoom to fits. Okay, and then you have your create instance. This is how we're going to create our different instances, our devices. And then these are your create wires, create wire name, that's how you label your wires. And then you're going to see this create pin. And a pin is basically used to set your input, output, or input output so that you could connect everything and all the different hierarchies. Okay? So let's get started with the instance. So first thing we're going to see is this add instance. Doesn't really tell us much, not very useful right now. What we really care about is the component browser over here. It always kind of defaults to the 50 nanometer library. We're not going to use that. We're going to come over here to the analog parts. Okay. You're going to see a whole bunch of different categories for us. So you're going to see we have N transistors and P transistors and resistors, inductor, capacitors, and supply nets, voltage sources. So we're going to build a standard CMOS inverter. So we're going to need PMOS. So as you'll see, a bunch of different selections for PMOSs here, and basically P-type transistors. What we're going to be using for this lab is the PMOS 4. So basically four points, right? We get gate, source, drain, and body. Okay, now that we've selected that, the add instance parameter screen is a little more useful to us now. So the one that we really care about, the two that we really care about, is going to be the length and the width. Okay. So as you can see here, the length, the minimum we can use for our 45 nanometer technology is 50 nanometers, okay? And the minimum width is 90 nanometers. So we're going to build a 2-to-1 CMOS inverter, okay? So let's go ahead and adjust the width on our PMOS to 180 nanometers. The hide. Okay, there we go. We just placed it. So it'll allow you to place a second one. To get out of doing that, just hit the escape button. Kind of backs you out. Okay. Now let's create another instance for our NMOS. Same thing, NMOS 4. And since it's a 2-to-1, we'll leave the width alone here. And escape. Okay, there we go. Now let's connect these things up. So add a wire, go ahead and hide that out of the way. Okay, so since we're dealing with a PMOS here, we're going to go ahead and connect the body to VDD, okay? And for an NMOS, we're going to connect the body to ground. Okay, so looks like we need a ground and VDD. So we need a ground and a source. Okay, so when you start off in the schematic, you set up ground and you basically set up your ground and your voltage source a little different due to the hierarchies. You'll see what I mean. But basically in the schematic, you're going to want to come over here, add an instance, open up the component screen. And we're going to want to actually add supply nets down in the lower schematic. Okay, so we're going to use ground, escape, and VDD. Escape. And now we want to add our inputs and outputs. So let's call our input A. This is where you select as an input. And then select our output as Y. And make sure we change the direction. Escape. And there you go. So now that is our basic CMOS inverter. Okay, so the next step, we're going to create a symbol for that, so that when we design a test bench, the symbol will represent this. Okay. Before we do that, though, it's probably a good idea to save this and check it. Okay, so we're gonna check and save, and as you could see, there was no screen, a box that popped up or anything giving us any kind of errors. That's a good thing. Okay, so if you actually came over to the log screen, you'll see that schematic check completed with no errors. But watch, if I actually come over here to delete and I take this wire out, and now we do a check save, you'll get the schematic check box that tells you that there was 0 errors but a warning found. Okay, if we come over to the log, you'll see pin G on P0, so that's basically your gate on pin 0, excuse me, your gate on instance P0, your gate on your PMOS as a floating input. Okay, so it's very useful. And also you'll see this too as well. It kind of does this, it highlights the area with the problem. So let's go ahead and fix that. Okay, nothing popped up, so we're good to go. Now we're going to want to come over here, create cell view from cell view. And this is all good, stay the same, right? It's basically from schematic to view name symbol. And this is basically how we're going to create a symbol that within it is this inverter. Okay. Select OK. Okay, so this is how what pops up. Okay, so this is basically your input and your output. Couple things we'll want to change here. You don't have to change some. You're always going to change the name, but you know, if you're building just something and having a box on the outside, you know, this green box represent, you know, be your symbol. If that's fine with you, you could just leave it the way it is and change the name to say, you know, and or invert, you know, inverter, whatever you're building. Okay. If you actually want the symbol to match what we're used to seeing and what we know in the inverter symbol is, which is a, you know, triangle, you can actually do that here. Okay. So you'll see up here that you can actually add circles and polygons and whatnot to create the symbol you like and prefer. So I'll go ahead and do that here. Okay, so the first thing I'm going to do is change the name. Okay, I'd rather this say inverter. So select it, come up to edit properties, and then just change the label. So inverter. Now want to select the, let's see if I can get it selected correctly. There we go. So select the whole box, delete it, and then now I'm going to create what I want to create. There we go. I like that a lot better. You know, this is actually a buffer, but so I'm not going to put the, you know, the bubble here, but you get the idea. Whatever you want to make, whatever you're comfortable with. So I'm going to go ahead and save this. Okay, great. So now close out, close this out, and we'll refresh our library screen. Okay, so now you saw what popped over here. Okay, so this is our inverter test library. Inside it we have a cell name inverter, you know, test 1, and then now we have a schematic and a symbol, and those are what we just created. Okay, so now that we have that set up, we need a test bench where we could call the symbol which contains the inverter inside it, and then, you know, build other things, and then run simulations. Okay, so what we're going to want to do, File, New, Cell View, and then what I like to do is Test Bench. So it'll be in this library, and this will now be our test bench, and we want it to be a schematic as well. Okay, so the first thing we'll do is we're going to call our instance up. Okay. Come over here, instead of going to analog parts this time though, we're going to go down to our own library, okay, our inverter test. And now we see inverter underscore test 1, and there you go. That's what we just created. And inside it is our CMOS inverter. Escape. Okay, great. So now let's build a simple circuit here, okay? So first thing we want to do let's go back to our analog parts. Add a capacitor. So this is the RLC cap. You can change the size of the capacitor. I'll make it a little smaller here. Not sure why that's not going away, but anyway. Okay, escape. Add a voltage source, or excuse me, let me correct myself there. Let's add a signal source. So analog parts. So this time in the test bench we're going to actually use voltage sources, not supply nets. So we'll come in here and you have, you know, VDC, and you have pulse and piecewise, and so I'm going to go ahead and use the piecewise. These are pretty awesome. Okay, so you'll see here it defaults to the number of pair of points as 2. You can actually change that, and it'll give you, you know, more down here. So let's go ahead and change that to 3. And actually it will now give us 3 below. Okay, so for the first one, let's start with at time 0, we want this thing to be 1.2 volts. Okay, that's what we're going to be working with here. At time 5 nanoseconds, we'll be at 1.2 as well. But then at 5.1 nanoseconds, let's go down to 0, okay? Hide that, connect this to the input, escape. So now we want to label our ground, okay? So standard is GND exclamation point. There we go. Okay, so we got our signal coming in here to our CMOS inverter, and then we have a capacitor on the output. Once you guys get into lab 2, you're going to get into some of the fan out and whatnot. So when you get like a fan out of 0, you're basically going to want to be using a capacitor equal to 0. I know that's a weird thought, but if you don't, you have like an open node here and it won't allow you to simulate. So when you have a fan out of 0, you're basically just wanting to get what the output of the CMOS inverter is without any load connected to it. So that's just a little trick to use. So just keep that in mind. That's a little more than our introduction right now, but just thought I would share that. Okay, so we do have our signal source set up, but as you can tell, we don't have any power to our PMOS or NMOS, right? I mean, there's, our PMOS doesn't have a voltage source, and our NMOS doesn't really have. Well, let me back off that. Mostly, we're concerned about our PMOS, so I'll leave that one alone. But what we're going to do is go ahead and build our power for the inverter. So VDC, and what we want to use is, you have a choice of AC or DC. We're going to use 1.2 volts. You guys already know about GND exclamation point, so we're going to be using VDD exclamation point for our positive. Okay, and basically what's going to happen here is this output here to VDD exclamation point is going to go to anywhere we have a supply net set up with VDD. Okay, so that's the inside of our CMOS inverter. Also, it will, for ground, to do the same thing. Okay, so the GND exclamation point will basically set up any supply net that's a ground supply net and kind of connect them to ground the way they're supposed to. Okay. Another useful feature when you're out here is to be able to, rather than have to go back out to your library and open up your schematic to see your CMOS inverter, you can actually do a hierarchy descend. So if you come over here to edit, hierarchy, descend edit, and then you actually select your inverter, you can actually put new tab, and you can pick schematic or layout much later when we get to layout. But for now, schematic, hit OK, and then bam, there's the inside of your inverter. And then you can just come back over here to test bench. Okay, so I think we're all set up to run a basic simulation. Okay, so what we're going to want to do now is come up over here to launch, and we're going to use the ADEL, and basically it's analog design environment. And I'll also always say that you can't get a license for that. And, just go ahead and hit yes. There's other different design environments. I prefer this one. Okay, so you could look around and choose the one that you prefer. Okay, so first of all, you want to set up your model libraries. Okay, and you want to come over here, double click, browse, and you're going to want to select your 50 nanometer model file. Okay, okay, come over here to choose analysis. You're going to be able to use transient, DC, AC, whatever you want to use. We're going to use transient right now. And the stop time, let's put 10 nanoseconds. And then now we want to select our outputs to be plotted. Select on schematic. Okay, so if you select a node, it's going to give you current. Okay. If you actually select the wire, it will give you voltage. And you'll see what I mean here. So I just selected the wire because we want to see the input and the output. It doesn't actually really show you here, but I'll show you. But basically this is going to be voltages, these nets. If you go back and I select, say, a node here, you'll see that it actually gives you a current. Okay, I don't really care about that right now, but just good to know. Okay, now that that's set up, oh, you know, something very important here. Did not save, check and save. Okay. Okay, it'll take a little bit of time for the graph to pop up. Just give it a second. Okay, there we go. Here's our graph. You can see that net 1 is our output, net 5 is our input. Okay, so you see net 5 is high, and then it transitions to low, and then our inverter does exactly what we want. It does the opposite, right? So we set up everything. Everything looks great here. It's sitting at 1.2 volts, just like we want, based on our power supply. You can see that there's some propagation delay. You can see that there's a little bit of rise time going on there. There are a couple things in here that'll help us to view this better and make this a little bit more user-friendly of a graph for us. So I'll walk through a couple of those right now. So back on the schematic, you can actually change your net names to something more like input, output, or if you prefer A, Y, whatever. And then when you're in the actual graph here, if you double-click net 1, you can actually change the lines up so you could see them a little bit better. So excuse me, the symbols. So I'm sorry. Type style. So over here on dotted, so I like to use dashed. Make it something that pops a little bit more. So let's go with pink. And then you can also bold it. Let's hit OK. See what that looks like. Much better. Yeah, I like that a lot better. And you can do the same thing with net 5. So let's make that green. hashed. Bold. Okay. That's a lot cleaner. I like that. A couple other things that are pretty useful here is when you start getting into wanting to look at propagation delays, you need to zoom in here. So this is a really useful way of zooming in. Kind of select the area, click once here, drag it out, and then it'll zoom in there. And then if you want to actually see what a propagation delay is, there's also a drop a marker. Excuse me, a cursor. Whoops. So we want to use a delta cursor. It'll actually give us two cursors, and you can actually set it up at your 50% mark and get your difference, right? Your delta. Okay, so there's a propagation delay of 32.88 picoseconds. And you can see that one starts at 5 nanoseconds, and the other 5.05, and the other one at 5.083 nanoseconds, and then this automatically subtracts them. So it's a useful little feature, to start getting your propagation delays. Then you'll have to use them for your rise times and fall times. Also, if you start getting into more signals and you don't want them all overlapped on top of each other, if you come over here to Axis, Strips, it actually separates them. So this could be very useful when you're starting to look at clocking numbers through. You probably won't get to any of that till later in the term, but it's very useful. So anyway, those are some ways to manipulate the graph. The one last useful feature that you'll get to later in the term will be using the calculator. So let's go ahead and just give that a shot real quick here. So let's select net 1, okay, and it tops off at it's a step function with the upper limit being 1.2 volts, our power supply. So let's open this up. This is our calculator. And when you select net 1, you'll see it kind of pop up here in the calculator. Well, you can do all kinds of different things. There's all kinds of different functions, and you can actually calculate the power and then plot the power and do an integral to actually figure out what the power is, and all kinds of other useful things. But just for something real basic here, I could come over here to the end and just multiply that signal by 2. Okay, so let's double it, and then click evaluate. And now you'll see down here that net 1 has now been doubled. Okay, so now it's going up to about 2.4, 2.5. Okay, so all I did was double the step function. So the calculator can do some very useful things for you, especially with power, like I said, and some other things. So there you go. I think that just about covers it. Okay, for an introduction to starting Cadence, remotely logging in, building a simple circuit, building a symbol for a simple circuit, and then running a simulation. Thank you.